Okay, so let us start the fourth section. Limsup, liminf and limit points. Limsup denotes limit superior, liminf denotes limit inferior. We will see what these things are. So I think in the previous analysis video, towards the end of the video, we considered this sequence. So let's start with this. Now in this sequence, as we saw previously also, the terms are alternately positive and negative real numbers, and the number of zeros between these two ones increases one by one as we go down the sequence. Now if one plots these real numbers on the real line, one gets a diagram like this. Note that half the terms of the sequence lie to the left of 0, they are negative, and in fact to the left of -1, all of the negative terms are actually strictly less than -1, because we have -1 and minus something else, -1 minus 0.01, -1 minus 0.0001. No matter how small that extra something is, that is also negative. So all the terms that are negative are less than -1, and like that all the terms that are positive are actually greater than 1 plus 1. So one can see that this sequence is not convergent, and in fact it does not in particular converge to 1 or -1. Why that is so? It's because you see, converging to had the sequence been convergent to 1, for every epsilon greater than 0, we would have found one positive integer n, such that if you are denoting the terms of this sequence by an, then this would have to be the case for all n greater than or equal to that positive integer n. But that is not possible. Why? Because you see, if you choose this epsilon to be, say, 1 over 2, then the distance between an and 1 is less than or equal to 1 over 2 if and only if an lies here within a distance of 1 over 2 from 1. Now there are terms in the sequence that lie in this interval, which are actually the positive terms of the sequence, but the sequence also has negative terms, and you see, because the terms are appearing in the sequence alternately, positive, negative, like that, so you will never be able to get rid of the negative terms no matter how far down the sequence you go, and that is, no matter how many terms you remove from the beginning of the sequence, you will always have negative terms left in the remaining sequence. So there is no getting around this. So that's why the sequence does not converge to 1. 1 is not a limit of the sequence. Like that, the sequence is not also convergent to -1. For a similar reason, you will not be able to get a positive integer n for which the terms of the sequence are consistently close to -1. How close? Say 1 over 2 close. Starting from that stage onwards, such a stage can never be found, and for that the positive terms will create problem. So that's why you can see that this sequence neither converges to 1 nor converges to -1. In fact, this is not a Cauchy sequence, so it cannot be convergent at all. For example, because of this positive negative problem, the sequence is not eventually 1/2 steady. So how can it be a Cauchy sequence? So that's why it cannot be convergent also. However, despite this, we see that these two particular real numbers 1 and -1 exhibit the behavior that they want to be limits. They are not limits, but they want to be limits, maybe not of the whole sequence, but parts of it. 1 seems to be the limit of this part of the sequence, and -1 seems to be the limit of the negative part of the sequence. These things give rise to the concept of limit points. So that is our first definition here. Definition 641, limit point or points. Let an be a sequence of real numbers. Let x be a real number. And let epsilon be a positive real number. Okay, just like the definition of the limit of a convergent sequence and also the definition of a Cauchy sequence, without giving this the entire condition of the definition of a limit point of a sequence, we will give it in parts. So like what we first did, when we defined the limit of a convergent sequence, we first defined what it means for a sequence to be epsilon close to a real number, then eventually epsilon close to a real number, and then finally convergent to that real number. So like that, here we are going to give the definition in stages. First we define what it means for this real number to be epsilon close to, or no, not epsilon close, epsilon adherent to this sequence. Epsilon close is something else, okay, and epsilon adherent is another notion. So let us see. We say that x is epsilon adherent to this sequence if there exists an integer n greater than or equal to m such that an is epsilon close to x. Okay, only that an, that single term is epsilon close to x. We say that x is continually epsilon adherent to our sequence if x is epsilon adherent to this sequence, for all integers n greater than or equal to m. Okay, so that is continually epsilon adherent. And finally, we say that x is a limit point or an adherent point of the sequence if x is continually epsilon adherent Okay, let me write let us not lose this part yet. Let me continue from here. X is epsilon adherent, continually epsilon adherent to the sequence for all epsilon greater than 0. Okay, so let us now try to understand what this thing means. First of all, say a sequence is given to us. So we have its terms like this: am. To simplify matters, let's take a specific value of m, say m equal to 1. Then we have a1, a2, a3, etc. So this is our sequence. So the first part of the definition says that x is a real number, and we are also having another thing, epsilon. We say that x is epsilon adherent to this sequence if there exists some index n. If there exists some index n, of course greater than or equal to m, because m here is the index from where things start, such that an is epsilon close to x. That is, the distance between an and x is less than or equal to epsilon. Just that n. Okay, if such an n exists, we say that x is epsilon adherent to this sequence. That means x is epsilon adherent to the sequence if x is epsilon close to at least one term of the sequence. An being epsilon close to x and x being epsilon close to an, they are the same thing. They just mean this inequality. Right. Now, the next part of the definition says that x is said to be continually epsilon adherent to our sequence if x is epsilon adherent to this sequence where the index is starting from capital N for all n greater than or equal to m. It means that if from our original sequence we remove some terms from the beginning, say we remove these terms, an minus 1, and these, after that we have the remaining terms, and so on. these terms have been removed. So whatever is remaining, x is epsilon adherent to that. That means x becomes close to some term here. Okay, and this continues. From this also, if you remove some finitely many terms from the beginning, then that remaining sequence also has the property that x is close to something from there. Okay, and it continues without any end. The fact that we can choose this capital N means that we can in fact remove as many terms as we want from the original sequence. Finitely many, of course, not infinitely many, but still x will find something in the remaining sequence to which it is close. How close? Epsilon close. And if now we vary epsilon also, then we say that x is a limit point of the original sequence or an adherent point of the original sequence. Clear? Should we see these things in this example? Let us see. For example, say you take epsilon equal to 1/2. Okay, this particular value of epsilon, suppose we have considered, and say our x is -1. So this is our x, and the sequence of course is this sequence. Now is -1/2 adherent to this sequence? Yes, of course. For example, the distance between -1 and -1.01 is what? 0.01, which is less than 1/2, which is 0.5. So that's why -1 is epsilon adherent to 1/2 adherent to the original sequence. In fact, -1 is continually 1/2 adherent. Why? Because you see, if you look at the negative terms of this sequence, the negative terms start here -1.01, and actually the negative terms are getting closer and closer to -1. The next negative term is -1.0001. So it is closer to -1 than -1.01, and the further down the sequence you go, the closer it will get to -1. So in fact, it does not matter how many terms we remove from the beginning of this sequence. Actually, we have better terms. Okay, terms which are more close to -1 than the previous terms. So we will never run out of terms in the sequence even after such a removal, that -1 will be close to that term. So we will always find such terms, and that's why -1 is 1/2 adherent to the original sequence, and in fact continually 1/2 adherent. And if one notices, one can prove this also, that it's not true just for this value 1/2, it's true for any positive real number epsilon. And that's why -1 is a limit point of this sequence. A similar argument will show that 1 is also a limit point of this sequence. Now there is a remark. After this definition, The remark is non-mathematical, but nevertheless it's there. The verb to add here means much the same as to stick to something. Hence the term adhesive. Okay, so now if we apply all the conditions in the previous definition at once to a sequence, what would that look like? Unwrapping all the definitions. All the definitions means all the parts of the previous definition. We see that x is a limit point of the sequence an, where n varies from m to infinity, if for every positive real number epsilon and every integer n greater than or equal to n, there exists an integer n greater than or equal to n, such that an is epsilon close to x, or in other words an minus x is less than or equal to epsilon. Okay, so you can see that this is something quite different from eventual epsilon closeness, which we see in the definition of the limit of a convergent sequence. That is something, and this is something else. In fact, regarding this, the author has to say some things. Note the difference between x being epsilon adherent, or okay, so he started with epsilon close. Difference between a sequence being epsilon close to L where L is some real number, of course, which means that all the terms, all the elements of the sequence stay within a distance of epsilon from L. So this epsilon closeness of a sequence of the entire sequence to some real number L is the first part in the definition of the limit of a convergent sequence. Recall that. So note the difference between a sequence being epsilon close to L and L being epsilon adherent to the sequence. Which means that some element of the sequence stay within a distance of epsilon from L. So the difference is in the quantifier. For all elements of the sequence, something has to happen here and here. For at least one element of the sequence, that same thing has to happen. That the corresponding term has to be epsilon close to L. For all, for at least one. And also there is something else. Also, see, these places may be quite confusing at first, but once you go through them again and again, things will fall in place. Also, for L to be continually epsilon adherent to the sequence, to say, since we have to specifically say what the condition is, so we are mentioning the sequence. Also, for L to be continually epsilon adherent to this, L should be epsilon adherent to this sequence for all n greater than or equal to m, whereas for this sequence to be, what is the corresponding notion in the definition of limit? Here we have continual epsilon adherence, Here we have eventual epsilon closeness. For the sequence to be eventually epsilon close to L, this sequence where the index starts from capital L should be epsilon close to L for some n greater than or equal to m. Do you see why it is confusing? In the case of epsilon adherence of a real number to a sequence, the quantifier is for some, for at least one. Here, epsilon adherent to the sequence, which means that some element of the sequence stay within a distance of epsilon from L. Whereas for epsilon closeness of an entire sequence to a real number, that same condition should be true for all. However, when we come to continual epsilon adherence and correspondingly eventual epsilon closeness, then in case of continual epsilon adherence, L should be epsilon adherent to these sequences for all. This time it becomes for all n greater than or equal to m. Whereas for the sequence to be eventually epsilon close to L, such a condition that this is epsilon close to L, that this sequence being epsilon close to L should be true for some, for at least one n. You find one n for which this is true, that's enough. Note one more thing, that this sequence being epsilon close to L is one notion, whereas this sequence, or rather L being epsilon adherent to this sequence, is an entirely different notion. Okay. First of all, these things should be clear. Okay, now moving on. Once you, I should not say memorize, but once you understand the definition of a limit point of a sequence or an adherent point, you don't need to think of these parts, that is epsilon adherent to the sequence or continually epsilon adherent. You can think of the notion of limit point just like the notion of limit of a convergent sequence at once. Okay, what we showed there, unwrapping all the parts of the definition. Now note one more thing, or okay, let us complete this paragraph. Thus, there are some subtle differences in quantifiers, that is this for all, for some, quantifiers between limits and limit points. Note that you may have noticed one more thing. Just like we defined the limit of a sequence, of a convergent sequence of course, to be a real number. Whenever it exists, it is a real number. Like that, a limit point of a sequence of real numbers has also been defined to be a real number. It's not plus infinity or minus infinity. In the definition, in the first definition, we have considered a sequence and we are saying that a real number x is said to be a limit point or an adherent point of the sequence if so and so conditions are true. However, this can be extended to include plus and minus infinity. We will see this thing in the exercises. Note that limit points have only been defined to be finite real numbers. Real numbers of course are by their very nature finite, but we are additionally mentioning finite to stress the fact that the x in the definition of a limit point is not an arbitrary extended real number. In particular, it's neither plus infinity nor minus infinity. It's a finite real, it's a real number. It is also possible to rigorously define the concept of plus infinity and minus infinity being limit points. See exercise 648. We will see this extension of the definition of a limit point when we get to that exercise. Let me first put some ink. Okay, so fine, the definition of limit point is not that straightforward. Okay, just like the definition of the limit of a sequence, it has some conditions. So let us now look at some examples that will illustrate this notion. Example 3. Let an where n is varying from 1 to infinity be the sequence what sequence 0.9 so the number of nines increases one by one. Okay, so this is the sequence. The number is 0.1 adherent to this sequence. And why is that so? What is the term of this sequence to which 0.8 is close, 0.1 close? And that term you can see clearly is 0.9, because the absolute difference between 0.9 and 0.8 is in fact equal to 0.1. Okay, since 0.8 is 0.1 close to 0.9, and 0.9 is a member of this sequence, so the number needs to be 0.1 close to at least some term. So we have found one such term. So that means 0.8 is 0.1 adherent to the entire sequence. However, (0.8) is not continually 0.1 adherent to this sequence. What is the reason? That's because continual 0.1 adherence means no matter how many terms we remove from the beginning of the sequence, 0.8 should be able to find at least one term in the remaining part of the sequence after the removal, to which it can become 0.1 close. Removal of the first term itself makes 0.8 lose that property. So you can see this sequence, since once one discards the first element of the sequence, which is 0.9, there is no element or let's write like this, there is no element left for 0.8 to be 0.1 close to. Okay, so although 0.8 is 0.1 adherent to the entire sequence, it's not continually 0.1 adherent to the sequence. And that's why, in particular, (0.8) is not a limit point. Of this sequence. For it to be a limit point, it should have been not only continually 0.1 adherent, but also continually epsilon adherent for any positive epsilon. So that is not possible, so 0.8 is not a limit point of the sequence. On the other hand, the number 1 is in fact continually 0.1 adherent. Okay, so the author has gone in stages. The number 1 is first of all 0.1 adherent to this sequence. Okay, if you ask what is the term in the sequence or the element in the sequence to which 1 is 0.1 close, you can take the example of 0.99 because this difference is 0.01 and this in fact is strictly less than 0.1. Okay, and the fact that this is not just 0.1 adherent but continually 0.1 adherent to the sequence, this real number 1, depends on the fact that actually if you take differences of 1 and the other terms, the further down the sequence you go, the difference actually keeps diminishing. So you are in a more convenient position actually. The more terms you remove, the difference between the remaining terms and 1, they all become far less. Okay, they become lesser and lesser. So all of them are less than 0.1, and in fact from the pattern of this thing, that is, if you for example remove the first 2 terms, then the largest difference between 1 and the terms and the remaining terms is 0.001. The other differences are even smaller. So the differences themselves are decreasing. So you can see that the differences can be made actually as small as you want, and this allows us to in fact claim that 1 is not only a 0.1 adherent to this sequence and not only continually 0.1 adherent to this sequence, but actually continually epsilon adherent to this sequence for any positive epsilon, because those differences can be made smaller than any epsilon. Okay, so you will always find something in the remaining sequence from which 1 is at a distance less than epsilon. Okay, so what were we writing? This is to this sequence, and in fact one is continually 0.1 adherent to this sequence. And what about that? Oh, so the reason has also been written here, since the reason is just that since no matter how many terms or elements from the sequence one removes, one always finds a term that is 0.1 close to 1. And in fact, yes, one is continually epsilon adherent to this sequence for every epsilon greater than 0. Hence, 1 is a limit point of this sequence. So 0.8, although it becomes 0.1 adherent to the entire sequence, but in the very next step it fails. However, 1 passes all the tests and it becomes a limit point of this sequence. Then there is another and that another one is our first example. So this is 644. So we are now going to say some relevant things about that sequence where the terms alternate between positive and negative real numbers. Now consider the sequence so it starts with 1.1 and minus 1.01, 1.001, and let's write another one, and so on. The number 1 we can write here also. The number 1 is 0.1 adherent to this sequence. Because the very first term is 0.1 close to 1. The difference is in fact equal to 0.1. Okay. In fact, actually whatever we said a few moments ago, we are just going to repeat those things. In fact, it is continually (0.1) adherent to this sequence, because no matter how many terms one discards from the sequence. One always finds a term that is 0.1 close to 1, and we are not writing this just for the sake of writing, because we have written a similar thing here. You can actually see, and in fact we have seen this once before, why this is true. The difference between 1 and 1.1 is 0.1, of course, but that difference keeps diminishing as you take the other terms. The difference between 1 and 1.001 is 0.001. The difference between 1 and this one is 0.00001. So it is much smaller than the other differences. So if you remove finitely many terms from this original sequence, no matter how many, that can be a million, a billion, a trillion number of terms, actually you are creating much smaller differences, in fact, than 0.1. So naturally one will be continually 0.1 adherent to the sequence. That's what we have written. And as was discussed earlier, one does not need all the elements, yes. All the elements are all the terms of the sequence. Of the sequence means even after such a removal of the remaining sequence to be 0.1 close to 1. Just some, that means at least one. Thus 0.1 adherent is weaker than 0.1 close, because 0.1 closeness demands much more than 0.1 adherence. 0.1 adherence demands that only one term be 0.1 close to the number, real number 1, whereas 0.1 close demands that all the terms be 0.1 close to 1. So it is weaker, it demands much less than 0.1 close, and continually 0.1 adherent. What am I writing? Adherent is a different notion than eventually 0.1 close. in fact, one is, oh, we don't have eventual here. One is continually epsilon adherent to this sequence for every epsilon greater than 0, and that's why 1 is in fact a limit point. This we have seen before. Yes, and so 1 is a limit point of this sequence. Similarly, -1 is also a limit point of this sequence. Whatever we have argued with 1 in mind, we can also do it with -1, and one will come to the conclusion that -1 is also a limit point of the sequence. And now if you look at this thing, okay, so we have gone through all the conditions and everything. Now again, if we think of the situation informally when we say that a sequence is convergent and has limits say L, then the terms of the sequence get close to L. That's the most vague way of saying this. When we say that L is a limit point of a sequence, then the terms of the sequence get close to L, but not in that manner. A part of the sequence gets close to L. It's like you have a bunch of particles, okay, on a line or whatever, infinitely many particles on a line, and says suddenly something else appears there near those particles. If that L turns out to be a limit of that sequence of particles, then those particles will get attracted to L, okay, in the sense that almost the entire sequence gets attracted to L. Some of the particles that are somewhat far away from L than the others will stop here. They will no longer feel the attraction. They have gone somewhat close to L and they have stopped. But the ones that are closer to L than these ones, they will continue to feel the attraction and they will also move towards L a little bit more, and like that the entire sequence moves towards L. Okay, this is an analogy only. Now if in place of this you put L here somewhere, then a part of the sequence comes towards L. However, maybe there are infinitely many other particles which are so far away from L that they don't feel any attraction at all. Something else, some L prime is say put there. Now that part will feel the attraction, so the points will locally accumulate here near L. Some other points will locally accumulate here near L prime. So this is the notion of limit and this is the notion of limit points. However, clearly you can see that the two notions are somehow related, and don't you feel that when L becomes the limit of a sequence, it should also be a limit point, and in fact that turns out to be true. So that is the first proposition or the first result of this section. So this is proposition 6, 4, 5. Limits are limit points. Limits occurs when they exist. Actually, this much is enough for us to understand what this proposition is going to say. It's going to say that if we have a convergent sequence with with a limit, a convergent sequence means it will have some limit, then that limit will also be a limit point of the sequence. So the statement goes like this: let an, where n varies from m to infinity, be a sequence of real numbers which convert. Sometimes we will not write of real numbers, okay, because at this stage we are dealing only with sequences that where the terms are real numbers, unless of course they are further restricted in some way, say a sequence of rational numbers, that we are not dealing with say sequences of vectors or sequences of functions. So that's why sometimes we will drop this part of real numbers, which converges to a real number C. Then C is a limit point. Then C is a limit point of the sequence, and in fact C is the only limit point. In that case, the limit point also becomes unique, just like the limit. And the proof, as usual, we will not do it now. We will see it in the first exercise at the end of this section. Okay, so far we have seen the notion of limit points. Now we are going to look at some other things, namely limit superior and limit inferior, which will turn out to be special types of limit points. Okay, so let's go through the definitions. If you are wondering why we need these things, aside from the fact that they are some interesting notions worthwhile to investigate, they will help us prove that the real line has no gaps. More specifically, they will help us prove that every Cauchy sequence of real numbers is convergent. The converse we have already seen, and it's not that difficult, that every convergent sequence of real numbers is Cauchy, but the other statement that every Cauchy sequence of real numbers is convergent, that we will prove using these tools. Okay, so this is definition 6. Limit superior and limit inferior. Let an be a sequence of real numbers. Now from this sequence we are now going to define another sequence. In fact, two sequences. Let's see the first one first. We define a new sequence an. Okay, here n will also vary. Okay, yes, a capital N plus now what are these a n pluses? Where a n plus is defined to be the supremum of the sequence an where n varies from capital N. Okay, this is something we have already seen before in the previous section, that if a sequence is given, we know how to find its supremum. So that means what is this entire thing telling us? It tells us that this capital N is our choice. Our choice means, in fact, we have to choose it like this. First we will choose in capital N equal to M. For that choice, that is this thing, is actually the supremum of the original sequence. Then am plus 1 plus, this by definition is the supremum of this sequence. That is, if our original sequence looks like this, am plus 1, am plus 2, etc., then the first term of this new sequence is the supremum of the entire sequence. The second term is the supremum of the sequence obtained by removing the first term. Then the third term is the third term of this new sequence is the supremum of the sequence obtained by removing the first two terms. Then such removals continue. Okay, and you have less and less terms. Although there are infinitely many terms, but you have less and less terms in the original sequence. You keep track of all the suprema, and those suprema give you a sequence of suprema. This is that sequence. Okay. Okay, having defined this, we are now going to define the limit superior. Oh, but before that, these same things what I have said now, they are also parts of this definition. More informally, an plus is the supremum of the elements of the sequence from an onwards. We then define the limit superior of the original sequence an denoted like this: limsup n tends to infinity. If you are wondering what that noise is, it's train. Denoted like this by it is the infimum of this sequence. This is also going to be some sequence, so it is the infimum of this sequence. It may look quite confusing at first. Limit superior of the original sequence is the infimum of a sequence of suprema. Okay. When you see limit superior, first you consider suprema, and then you take the infimum of all the suprema. And similarly, limit inferior. Similarly, we define the sequence this time. We start by defining an minus by defining an minus to be, this time we start with inferiors. Infimum. I am also getting confused. Infimum of the sequence an where n starts with capital N. Define the sequence like this, and then define the limit inferior of the original sequence denoted like this liminf. So these are the things that we saw in the title of this section, limsup and liminf. These functions are available in LaTeX, okay, limsup and liminf, that mathematical typesetting software. To be this time, we have considered infinitely many infima. Now, of them, or rather of their sequence, of this sequence, we are going to consider the suprema, and that is the limit inferior. Okay, the definitions may look quite strange at first, but we will see why they have been defined like this and what is their purpose. We will see, but before that, let us now go through some examples and see in those examples some specific sequences, and let's calculate their limit superiors and limit inferiors. So this is the first example. Let A1, A2, A3, etc. denote the sequence. Oh, so it's our first sequence with which we started the video. Let's not write the other one. We have already seen it twice by now. Okay, so we start calculating. First of all, the sequence of all the suprema. Then the sequence A1 plus, A2 plus, A3 plus, etc. is what? What is A1 plus? A1 plus is by definition the supremum of the entire sequence. Keep in mind that since we have classes, so we are calculating supremum. So in the entire sequence, we have seen before that the largest term is 1.1. So that is the supremum. So it is 1.1. And then if you remove 1.1, if you remove the first term, then you are left with this remaining sequence. In this sequence, the largest term is 1.001. So A2 plus is 1.001. Then after that you remove one more to find A3 plus. Note that 1.001 is still there and it is still the largest element. So the next term is also this. Now only after that do we remove this 1.001. After that removal, The next largest is 1.00001. So that will be the next one. A4 plus. Now after A4 plus, what you will do, you will remove this one to find A5 plus. But removal of this keeps this. Okay, this does not go anywhere. So the next one is also this, and the sequence of suprema goes like this. And what is the infimum of this sequence? If one looks carefully, the infimum turns out to be 1. In fact, to claim that the infimum of this sequence of suprema is 1, one has to prove it, which can be proved quite easily. Hence, the limit superior of this sequence is 1. Okay. Similarly, now we want to calculate the limit inferior. So we will first of all calculate infinitely many infima by removing the terms one by one. So the sequence of infima a1 minus, a2 minus, a3 minus, and so on is, okay, what in this case, what is the sequence, original sequence, it turns out in fact has a smallest element, minus 1.01. So that is the infimum. Then after that, if we remove this 1.1, that process is the same. Okay, we have to remove the terms one by one. This term still is there. So a2 minus is also minus 1.01. And after the removal of this, the next one is this, second smallest. But then after removing this one, it still persists. So, and it goes like this, which has the supremum. Okay, now it's a sequence of infima. So we need to calculate its supremum, and its supremum, this also can be proved, is minus 1. Hence, the limit inferior of the original sequence is minus 1. Do you notice one thing? That the limit superior 1 and the limit inferior 1 turns out to be the limit points of this sequence. We have already found that these are two limit points of this sequence. And that's why we said before defining limit superior and limit inferior that they turn out to be special cases of limit points. This is not always the case. Sometimes limit superior and limit inferior, from the nature of these definitions you can see, they will be plus or minus infinity. We are going towards such examples. In that case, we can't say that they are limit points, because according to our definition, limit points as of now are real numbers. However, recall that we said there is an extension of the definition of limit points which allows us to include plus and minus infinity. Once we do that, then things will change. But before leaving this example, there is one more line. One should compare this limit superior and limit inferior with the ordinary supremum and infimum of the sequence which are 1.01 and no, it's not 1.01, it's 1.1 and minus 1.01 respectively. Then example 8. Now another sequence, let A1, A2, A3, etc. be the sequence of integers. Here also the terms alternate between positive and negative integers. 1 minus 2, 3 minus 4, 5 minus 6 and so on. 2 more, 7 minus 8, etc. So let's calculate the limit superior and limit inferior. The sequence A1 plus A2 plus A3 plus etc. is, okay, this time does the original sequence have any upper bound? No, because these terms, the odd integers which are positive, they keep on appearing without any bound and they are not bounded above. So that means the original sequence is not bounded above, in the sense that it does not have a real number upper bound. So that's why A1 plus is plus infinity. If you remove 1, you still have the other odd integers 3, 5, 7. They are not bounded above. So that sequence also has supremum plus infinity, A2 plus. And once you remove minus 2 also, still 3, 5, 7, they are there. So you can see that there is no getting rid of these positive odd integers, and as such the sequence of suprema is a constant sequence which has all the terms equal to plus infinity. And this makes you realize one more thing, that the sequence of suprema in general is actually not a sequence of real numbers. It's a sequence of extended real numbers. This is one example where none of the terms is a real number. However, it does not matter what the terms are, whether finite or infinite. We have everything covered. That's why we have one section before it which deals with extending the notion of supremum and infimum to the sequence of extended real numbers, not just for sequences of real numbers, because we need them here. So this is a constant sequence, and what is its infimum? So infimum is also plus infinity, hence the limit superior of the original sequence is plus infinity. On the other hand, the sequence of infima A1 minus A2 minus A3 minus and so on is the constant sequence, all of whose terms are minus infinity. And what is happening here is, see, now our attention comes to the negative integers, which are even integers. They are not bounded below. So that's why the original sequence has infimum minus infinity. And no matter how many terms we remove from the original sequence, we will always have negative even integers which are not bounded below. So that sequence will always have infimum minus infinity. So that's why the sequence of infima is constantly minus infinity. And this sequence has the supremum minus infinity. So the limit inferior of the original sequence is minus infinity. So here both the limit superior and limit inferior are infinite extended real numbers. Then example 9. Let A1, A2, A3, etc. be the sequence 1 minus 1 over 2, 1 over 3, minus 1 over 4, 1 over 5, minus 1 over 6. You get the pattern. It's the terms are those of the sequence 1 over n, but we alternate the sign between positive and negative. The sequence of suprema is, okay, in this case you have to be careful. First of all, when we are calculating supremum, if there are negative as well as positive terms, we ignore the negative terms. We don't think of them because the positives are always already greater than the negatives. So here the sequence has a largest term 1. So a1 plus is 1. Once you remove that 1, then a2 plus becomes 1 over 3. Then for a3 plus you will remove the first two terms. 1 over 3 is still there, so 1 over 3. And you can see that the other terms will be like this. And so on. So this is the sequence of all the suprema, which has the infimum 0. This also one can prove analytically, rigorously. So let us use the notation that we have in the definition. Limit superior of an is equal to 0. Okay, now next limit inferior. The sequence a1 minus a2 minus a3 minus etc. is, now this sequence, just like the original sequence has a largest term, it also has a smallest term, which is minus 1 over 2. So minus 1 over 2, this is the first infimum. After removing 1, it is still there. So minus 1 over 2, and then it will go like this. So it's a sequence of infima which has the supremum 0. So limit inferior is also 0. You can notice one thing, that the original sequence is actually a convergent sequence with limit 0, and we see that both the limit superior and limit inferior turn out to be equal to the limit. This in general is true. If your sequence is convergent, then the limit superior and limit inferior will be equal to the limit. And actually the converse is also true. If you have a sequence of real numbers whose limit superior and limit inferior are both real numbers and they are both equal, then the sequence is convergent and it converges to that common real number. This will be used in proving that every Cauchy sequence of real numbers is convergent. We will prove these things in the basic properties of limit superior and limit inferior at the end of these examples. Then there is one more. let this be the sequence of all positive integers. In this case, the sequence of suprema is what the original sequence is not bounded from above, and so you can see that also no matter how many terms you remove from the beginning, that unboundedness persists. So this is constantly plus infinity. Which has the infimum also plus infinity. Hence, limit superior is plus infinity. On the other hand, the sequence of infima is what? The original sequence has a smallest term, so that is the infimum. A1 minus is 1. If you remove 1, then the remaining sequence also has a smallest element, which is 2. So A2 minus is 2, like that A3 minus is 3, A4 minus is 4, and so on. So in this case, you see that this sequence of infima turns out to be actually equal to the original sequence. And what is the supremum of this? Which has the supremum plus infinity. So the limit inferior is also plus infinity. So limit inferior can be plus infinity. Okay, this is one such example. We will end this video with this remark. After the remark, there is one discussion which uses that piston analogy that we used in the previous section to describe the supremum and infimum of sequences. Such a piston analogy is there also available for the notion of limit superior and limit inferior. But we will get to those things in the next video. So the remark is this. The remark is about the notation, these notations, limsup and liminf. Some authors use the notation this. Instead of our limit superior notation like this, and this instead of and some people also call limit superior the upper limit of the sequence and limit inferior the lower limit of the sequence. These, however, have not been mentioned in this text, and we will not use those terms. Note that the starting index M of the sequence is irrelevant. Do you recall that in after going through the notion of limit of a convergent sequence, in one of the exercises we showed that that is, if you, for example, you have this sequence, right? It's a convergent sequence. We know that its limit is 0. Now, whether you start the sequence from 1 or you start the sequence from 1/4, it does not matter. The limit is still 0. So the starting index does not matter. In other words, the first few finitely many terms don't matter. Only the infinite tail end of the sequence matters. So the same here is also true when one calculates the limit superior and limit inferior of a sequence. The first few terms don't matter. So equivalently, the starting index M does not matter. For that, see the second exercise, where of course we will be asked to show that this is in fact the case, that no matter where you start, the limit superior and limit inferior of the sequence do not change. And once one finishes all these things, after that there is one proposition, I think it's proposition, which states the basic properties of limit superior and limit inferior, using which we can say many things. The fact that Cauchy sequences of real numbers are convergent is one consequence, is one example of those many things. So we will see these things in the next analysis video. And today is, what is the date today? 18. What, it's showing 19. Oh, that is because we already, already it's way past 12. 19, 20, so that means 18, 19, 20, 21. On 21 we will have our calculus video. I forgot about calculus actually. And tomorrow I will upload that Lee's algebra, abstract algebra exercises. Okay, so see you tomorrow. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.